Okay, good afternoon, all of you. My name is Dr. Nagaraju, Assistant Professor in the Department of Computer Science and Engineering, Artificial Intelligence and Machine Learning, Institute of Aeronautical Engineering, Dundigal. Today, I am here to explain you a most important topic in artificial intelligence, which is called as predicate logic. Predicate logic, or otherwise we can say that first order predicate logic also. In short, we will simply represent it as FOPL or FOPL. Means predicate logic or first order predicate logic is expressed in the same way. So first of all, before moving into learning what this predicate logic is, first of all let us have to see some of the objectives. Means today's objective during this session is I want to formulate some of the sentences in logic. In the previous session we have discussed that the representation of specific knowledge in the terms of logic is very important. So for that one, what are the essential elements required? By taking the help of those essential things, how we can represent the knowledge in the form of logic, that we will try to see with the help of some examples. Then we will try to introduce to the first order predicate logic, or simply we can say predicate logic. Here we are going to see multiple examples where we are going to understand how the English representations of knowledge can be converted into the mathematical form. Next, we are going to see how to write some of the correct predicate logic formulas. Then at the end, we are going to see about a specific topic which is also somewhat important while representing the statements in predicate form, that is well-formed formulas. So let us move ahead, and we will try to cover all these objectives in this session. First, before moving into the predicate logic, I want to give some review about this propositional logic. When we want to represent the knowledge in the form of some formulas, in the form of some mathematical formulas, so definitely you need to make use of some kind of variables and some kind of symbols. And also we have seen one important point, that is the representation of logic can be done only with the help of some formal languages. So for that one, there are two choices are there. One, you can select the propositional logic, or otherwise you can go for representation of predicate logic. Means these two, the propositional logic and predicate logic, these two are called as the language of logics. And also we can say that these are two formal languages which we will use in order to represent the knowledge in the mathematical form. So during our previous session, we have discussed that the propositional logic can also be used to represent some kind of knowledges in the form of mathematical symbols. But there are certain limitations in the propositional logic. Let us try to understand what are the limitations where the propositional logic has really failed. For that one, I want to explain all these things by taking some suitable examples. Okay, here what I have done is I have taken some sentences which are represented in the English form. So we will try to convert these English representations into some propositional logic representations. So for that one, if it is a sentence saying that James is a hardworking student, so generally how we represent this one, we represent that hardworking will become some kind of relation, and this hardworking we are talking all about James. So in the propositional logic, in the simple way, you can represent the statement saying as James is a hardworking student as simply hardworking and in the bracket James. Similar to that one, if the other statement, James is an intelligent student, so simply you can write it as here intelligent. Okay, who is intelligent here? James is intelligent. Okay, and the third one, you see, if James is hardworking and James is intelligent, then James score high marks. So if you want to represent this one in the propositional logic, generally we used to write like this. The same way how we have done in the above two examples. One is you have to say that hardworking. Who is hardworking here? James. And there is a connection here. This is called as a connector, which is connecting two different sentences here. So and we have to use a symbol called as conjunction symbol, which is also one of the propositional logic symbol. It is called as connective, or we can say that it is a logical operator which is used to connect two different sentences, or we can say two atomic sentences. So the first one means James is hardworking. But saying James is hardworking, I am representing it as like this: James hardworking James, and a conjunction symbol. And here one more sentence is also there, which is called as James is intelligent. So in this case, I will write like this: intelligent. Okay, who is intelligent? Again, the James is intelligent. Okay, means when the James is hardworking and James is intelligent, so what we are going to get means James is going to get high marks. So we can take it as like this: score high marks. Score high marks. Again, who is going to score? James is going to score. Okay, means in this one, what happened here? The symbol, it is conjunction symbol. It is called as employee symbol. By using these two symbols, right, in the propositional logic, we could able to convert this English representation in terms of some mathematical form. If you want to make it more clear, means more perfect mathematical form, then you can mention like this. You can consider this James is hardworking as P, James is intelligent as Q. If it is a case, so what happens? The mathematical representation will be like this. One is P and Q, that implies to some R, we can say. Okay, but here you try to observe, in the three examples, I am talking about a specific person which is called as James here. For example, if the class is having more number of students who are hardworking and who are intelligent, then how we are going to represent it? In the propositional logic, means in the propositional logic, we are failing to represent the same English sentences, right, which are in the generalized form. Means if you talk about this one, they are not generalized, they are specific. Why? Because I am talking only about one particular person called as James. But what happens if I want to represent the same sentences for Adam and Thomas? So again, what you have to do? Again, you need to write the same kind of representations. Means whenever I say James is hardworking student, then again I have to say that Adam is a hardworking student. Thomas is a hardworking student. For James also, the second statement also, James is an intelligent student. Okay, in place of James, then again what I have to do? I need to use Adam. Means Adam is an intelligent student. Similar to that one, Thomas is intelligent. So I should go on representing the same sentences for different people. Why? Because in the propositional logic, we have represented these English sentences not in the generalized form, but we made it as a specific one. But is it possible to represent such sentences in the mathematical form for each and every student? You should not supposed to do it. Why? Because there should be a standard mathematical representation which can be used for all the other similar kind of representations. Means if I mention some statement, that statement should be useful for any people. Either it can be a James, or it can be a Adam, or it can be a Thomas. Okay, and one more important observation we have to do is, for example, if there is a statement called as all men are mortal. All men are mortal. So generally, if it is a statement saying that a man is mortal, then we can represent it with a variable in propositional logic, that is P. Okay, but what happens about this all? How to represent this all in the mathematical form? Similar to that one, if I say that all the students are intelligent. All the students are intelligent. So what happens in the propositional logic? I can represent this sentence. What is that? Students are intelligent. If I say, one more example I will take. If I say few students got good jobs. Few students got good jobs. So in this case, what is happening? I am not talking all about the students. I am not talking about the number of students who are present in the class, but I am talking about only the few people present in the class. You try to observe the variation in these examples. In the first one, we are talking about all the people. In the second case also, we are talking about all the students. But in the third case, we are talking only about the few people of the students. So in the propositional logic, if you want to represent the sentences in the mathematical notation, it will be very hard to represent this all and very hard to represent few. Means there are few such kind of things are there. Means in these representations, what is happening? There are few words which are coming in the representations, that is like all and few. Okay. Sometimes what happens, we can in like all, right? Like all, it may be everyone. It may be everyone, right? For few, it may be someone. Means there is possibility of getting these words also while representing the English sentences. But with the help of propositional logic, how you are going to represent these words? All, few, everyone, and someone. Is it possible? It is not possible. Why? Because propositional logic is going to support only few connectors which you can use to connect different statements. The symbols there are, one is conjunction. Either you can use conjunction, or you can use distinction, or you can use negation, right? Or you can use sometimes implies, or you can also use double implies. Okay, of course, this also can be represented like this, and double implication also you can represent like this. So we are having only these symbols through which we have, by using these symbols, we have to represent all the English sentences given to us in the mathematical form. But for representing all and few, we don't have any such kind of symbols to represent. So in this particular case, we are failing to provide an association between these two. Simply we can say that men are mortal. You can, by using a variable p, you can represent it in the mathematical form. But how you are going to represent all? Means we are failing to provide a connection, or we can say association between this word and this sentence. So that is the biggest problem that arises while we are using propositional logic as a formal language. This important thing has made us to understand and to learn predicate logic, where we can represent even this kind of words also, like all, everyone, few, someone, like that. Okay, we will try to see some of the examples, and we will clearly understand, we will try to understand how there is a difference between the representation in the propositional logic and representation in the predicate logic. Okay, so here what happened? We have moved into an infinite model. We can say that it is an infinite model. Why? Because you see, you try to observe these examples, the same examples. One is, I am saying that James is hardworking. How you can represent in propositional logic? As P. Adam is hardworking. In this case also you can represent as Q. Thomas is also hardworking. So we are representing using some R. So whenever, if I say these three people are hardworking, so there is one possibility for me to represent in the propositional logic like this. What is that? P and Q and R. Means James is hardworking, and Adam is hardworking, and Thomas is also hardworking. But what happens if I want to represent the same sentence, that is saying that all students are hardworking? Okay, this is one of the example through which we can understand that the propositional logic is having some kind of limitations to represent the knowledge. So we have to go for the usage of predicate knowledge. That's why I am telling that propositional logic can handle only an infinite number of propositions. Why it is infinite? Because every time you are going for specific. Means if your class is having only James, Adams and Thomas, then this kind of representations is okay. But here what is happening? Here all the students, we are talking about all the students. Okay, whenever I am talking about all the students, that means that all the instances of a particular world. Okay, so then we can say that it is an infinite model. Why? Because James is hardworking, P, and Q and R. So what happens if some other student is also hardworking? Again, I need to keep some S. Okay, some T. I should go on representing like this. So here what is happening? We are moving into some kind of infinite loop. We are going into infinite loop. Why? Because all are talking about only one particular thing, that is about hardworking. Only the thing is, we are talking about a specific student in this case, and here we are talking about all the students. In the previous session also we discussed one important point. When you are representing the knowledge in the knowledge base, you have to see that your knowledge representation should be generalized. Generalized means the same kind of representation can be used for multiple purposes. You can use for multiple number of times, we can say. But whenever you mention these kind of things, it will not be used for other purposes. Means if I want to tell that other student is also intelligent, so in this case it is failing. I cannot use the same word same sentence James is hardworking, and I cannot apply it to some other student. Why? Because James is different and some other student is different. So why can't we have a common mathematical form through which we can explain saying that all the students of the class are intelligent, are hardworking? So this had made us to introduce new concepts, that is, along with propositional logic variables, we need to have some other things also, which is called as here quantifiers. Means if you see the difference between the propositional logic and predicate logic, the only difference is in the predicate logic we are going to see some quantifiers. Through quantifiers easily we could able to represent the words like all, for all, everyone, few, somebody, such kind of words we can represent. So let us try to see some examples and we will understand how we can represent the same things in the predicate logic. Okay, so first order logic or first order predicate logic, we can say it is used to represent the knowledge that cannot be reasonably be presented in propositional logic. Means which it is not possible, which is not made possible in propositional logic, that with the help of predicate logic we can do it. Okay. And one more important thing is, in predicate logic or in the propositional logic, we are going to deal with the real world facts. Means whenever you represent the real world facts as statements, then we can say that it is a well formed formulas. Okay, if it is James is hardworking, James is hardworking, if it is related to the real world fact, if it is a fact, then I can say that it is a well formed formula. Okay, we will take some other examples and we will try to understand what these well formed formulas are. First, we will talk about this predicate logic. So in this predicate logic, we are going to see some different terms. Means we need to understand some terminology so that it will become very easy to understand the other representations. The first one is objects. Objects are nothing but some things with individual identities. For example, if I take animal is, I can say cat is one object. Or if you think that this is general specific, then you can go for saying that animal is one of the object. Human is one of the object, vehicle is one of the object. So why I am saying these things as objects? Why? Because they are having some individual identities. They are having their own identities, or we can say they are having their own properties which will differentiate one object with the other object. Okay, so properties of objects are nothing but the same thing. Means if I want to differentiate, means how can I differentiate an animal with a human? And similarly, how can I differentiate a human with a vehicle? By the properties it carries. By the properties it carries. So they are nothing but the properties of the objects which we are going to use in order to differentiate between the objects. Only properties are going to tell that animal object is different and human object is different. And human object is different and vehicle object is different. So when you are using these objects, our primary duty is also to identify the properties of objects. Then only it is possible to differentiate one another. Next is relation. So what is the relation that exists between the objects? That is also very, very important. Okay, we can say that this is a kind of representing some association among the objects. Okay, human is there and vehicle is there. So what is the association between this human and vehicle? I can write it as drive. I can use it as drive. Here what the drive will becomes the relation. Okay, means when you want to represent something in the predicate logic, you need to understand what are the different objects. Okay, means which are called as objects, which are called as the properties of objects, and which are called as relations, and along with you need to have some other which is called as functions. Functions is nothing but subset of relations. Okay, I will show a simple a statement how these subsets can be represented. Of course, that we are not going to use it as an example in this session, but you try to understand this one. I can use this sentence saying that move, right? Move and some state. Some list of parameters will be there. Okay, this is one of the representation, knowledge representation using some predicate logic. So in this case, what happens now? This move is going to become the relation. This is going to become a relation, and this is going to become a function. Okay, for example, this function can be anything. For example, if you are talking about a human, right, this function can be walk. Okay, this function can be jump. Okay, this function can be run. Like this, you can go on representing the functions. Okay, so in place of move, you can write it as behavior. Behavior, or otherwise we can say action. Means you can represent the statements like this: action, right? Action and the state. For example, it is walk. So walk is going to have some kind of properties. That properties we will represent here, like this. So how many number of functions we are taking, those number of representations you can do it. That's why as we are having a chance to represent the knowledge in this way, we are saying that the functions are the subsets of relations. Let us try to understand what this first order predicate logic is going to provide us. Okay, the first one is constants. Constant is nothing but a name of a specific object. So I can say that 5 is a constant. I can say that Thomas is also a constant. Okay, like this, they are called as the constants, which is nothing but a name of a specific object. Even I can say that car is also a constant. Next, variables. Variables are nothing but it is going to refer to a particular object. Refer to a particular object without naming it. For example, you see the same example I will take. Thomas is hardworking. Thomas is hardworking. So in the representation, how you do it? You will you are going to write like this. How? Hardworking Thomas. Hardworking Thomas. So in this case, what I will do is, instead of using Thomas, I am going to write like this: hardworking some X. Hardworking X. So in this case, what happens? X is going to become this one, Thomas. Okay, that means here X is a variable which is going to refer this particular object. Refer this particular object without naming it. Okay, that is called as a variable here. And next is functions. Just now we have seen they are used in order to make the mappings between the objects. Nothing but exhibiting some kind of association, or explaining or representing some kind of association between the objects. And next, terms, which are nothing but referring to objects. Means terms are used to refer the objects. And atomic sentences. Atomic sentence means it is a unique sentence, remember. It is a unique sentence, or we can say that it is a single sentence. The output of these sentences can be either true or false. I can take the same example here. Thomas is hardworking. Right here, what is happening here? Thomas is also hardworking. Thomas is hardworking. We can say that this is also an atomic sentence. Atomic sentence or single sentence, both are same. Okay, so if I ask you, say this particular question, Thomas is hardworking, you are going to say either yes or no. Means for all these kind of representations, the outputs of these representations can be either true or it can be either false. Okay, we will try to see there are two different kinds of sentences we are going to use in predicate logic. One is called as atomic sentence and another one is called as composite sentence. That we will try to see with suitable examples. Coming to the predicate. So here, what do you mean by predicate here? The predicate with no variable, we can say that it is a proposition. The predicate with no variable is a proposition. So here what is happened? James is hardworking. We are not representing this James is hardworking with a variable. So I can say that James is hardworking is just a proposition, but it is not a predicate. Okay. So a predicate with one variable is called as a property. A predicate with one variable is called as a property. For example, you see player X. If I say player X is a predicate, so what happens here? It will be true. Means this statement is going to give us true when this X is a player. X is a player. Then only you are going to get true for this predicate. Similar to that one, student Y. For student Y representation also, you are going to get true when that Y is a student. Okay. For example, if I say X is a student, X is a student and Y is a player. If this is the actual fact and you have represented in this way, how? Player of Y. Okay, player of Y is okay, correct only. We will talk about this one, player of X. So if I represent player of X, actually what happened in the representation or in the knowledge base, we have mentioned that X is a student. But here we are talking about a player. X is not a player. So the output for this one will be false. Similar to that one, if I write student of Y. If I write student of Y, then it is also going to be false. Why? Because Y is not a student, but he is a player. Means for player X, you are going to get true when this X is a player. Similar to that one, you are going to get Y true. Sorry, you are going to get true when this Y is a student. Okay, that means that like functions, except that it is going to return true or false as the outputs. Means for predicates, you can expect true or false as the outcomes. Now you try to observe this particular thing. Here, gt of x comma y if is true if and only if x is greater than y. So in this one, we need to understand what is a function here. Okay, in this representation, I can say that gt is a function. Okay, or otherwise, for clear understanding, we can say that it is a predicate. Function or predicate. So what this is going to do? What this gt, we are using this gt. Gt is nothing but here greater than. Means whenever I write greater than x comma y, means gt x comma y, that means that I am comparing the value of x with a y. Okay, means I will take one example. How it is gt of 1 comma 0. If I represent gt of 1 comma 0, that means that I am doing a comparison between 1 and 0. 1 is greater than 0. So if it is a case, you are going to get the answer as true. If it is not the case, right, the answer you are going to get is false. If it is not the case. Similar to that gt, right, we are also going to have some lt also. Lt means to find out the less than. Gt means greater than and lt means less than. So if I represent lt of 1 comma 0, so what it means? 1 is less than 0. So the answer is not true. So the output you will get is false. Okay, like that it will work. So here gt is a function which is going to do a comparison between the two values, which is called as x and y. So the output of this particular sentence you are going to get true when the comparison is true. So like this, these are the two examples we can say, gt and lt. Okay, means gt of x comma y. If I say gt of x comma y, that means that I am talking about x is greater than y. If it is the case, you will see the true as output, otherwise false. Now we will try to see some of the examples, right, how to convert the English representations, or we can say some propositional logic representations into predicate logic. Okay, these are the examples we have taken from the textbook. So what is that one? First one is Marcus was a man. Okay, this is a sentence, so I want to represent in the propositional logic. Why I need propositional logic? Why I am using propositional logic means here there is no need of any predicate logic to represent it. Why? Because it is just a simple kind of proposition. If it is a proposition, easily you can mention like this. Marcus was a man. So I can write man Marcus. I can write man Marcus. Similar to that one, Marcus was a Pompeian. If really Marcus is a Pompeian, the same way I can represent just like I have done for the first one. So how can I write it? Pompeian. Who is Pompeian here? Marcus is the Pompeian. Why I am telling these things as propositional logics means we are having just single sentences. We are having just single sentences and we didn't come across with the words like all, someone, everyone, there exist, like kind of things. That's why even if you select propositional logic to represent this one, it will be okay. But what happened here, you see in the third case, we got a word called as all. Means here, it is talking about this thing, what all Pompeians were Romans. Earlier only I mentioned that we don't have any specific symbol to represent this all. So here, propositional logic does not work for us. We have to go for using predicate logic symbols. So how it will be? We are going to use a symbol which is called as for all and I am going to represent it with X. Means it indicates for all. So all whom I am talking about? I am talking about the Pompeians. So I have to represent in this way. Pompeian or Pompeians. Who are the Pompeians here? I am representing with X. So these Pompeians, who are these Pompeians? These Pompeians are Romans. These Pompeians are Romans, right? So this will be the way how we are going to represent all Pompeians were Romans in the predicate logic. Okay, Caesar was a ruler. When it is the case, so as there is no other words, all, for all, someone, there exist, such kind of words are not there. So using some propositional logic also you can represent this. So how it will be? Ruler, in the bracket you have to write who is that ruler? Caesar is the ruler. Okay, let us try to see some more examples so that we will get some expertise. We will become some expert, right, in writing these predicate logic statements. See here, all Pompeians were either loyal to Caesar or hated him. All Pompeians, just like we did for previous one, you have to represent like this. All X. X is talking about the Pompeians. So it is Pompeians. It is Pompeians X. Okay, Pompeians X. What they are? They are, okay, what action? They are loyal to. So loyal to. Who are loyal to? X. X nothing but Pompeians. Pompeians are loyal to whom? Loyal to Caesar. Loyal to Caesar. And some continuation is also there. What is that? Hated him. Okay, but here how it is? Or. Here or is a connector, remember. Or is a connector which is connecting some multiple statements here. So for or we are having disjunction. So this symbol is used as a disjunction. So what is happening here? Hated. Means who is hating who? Whom? Means Pompeians are hating the Caesar. So we are how we represented the Pompeians as X. So you have to write like this. X comma Caesar. X comma Caesar. Means for all X, X is representing all Pompeians. So what is Pompeians? Pompeians are, they were either loyal to the Caesar or hated the Caesar. They may be loyal or they may be hated him. So that's why you are going to represent in this way. Similar to that one, come here in the sixth example. Everyone is loyal to someone. Everyone, right? Means two different things comes in the same sentence. They came in the same sentence. Everyone, someone. So if it is everyone, we are going to write like this for all X. right? But what about someone? Someone means there is another symbol is there. There exists one more symbol which is called as like this. This is for all, for everyone, and this is for someone. Okay, right? So what is happening? They are loyal to. Okay, who are loyal to whom? Everyone are loyal to someone. Everyone we have represented with X, and someone we have represented with Y. So the representation will be like this. Come to the next example. People only try to assassinate rulers they are not loyal to. People, right? People means, is it all or is it someone? So definitely I am not talking about someone. People means everybody. So in that case, again the same thing. So why I am using X here? To represent the people. To represent people. So these people, okay, these people, and one more thing is also there. What is that? Rulers. One more thing, rulers is there. So I have to include that one also. So for all X and for all Y, for all X and for all Y. So we are talking about, we are taking X for representing the people, and we are taking Y to represent the rulers. And what they are trying to, okay, they are trying to assassinate. They are trying to assassinate. Who are trying to assassinate whom? X means people are trying to assassinate Y. Y means here rulers. And one more thing is also there. Are not loyal to. Of course, this representation is only up to this particular part. But we are not yet represented this sentence. Are not loyal to. So in that case, what is happening? Loyal to or not loyal to. When it is not loyal to, negation should be used. Not loyal to. Not loyal to. Who are not loyal to whom? X means people are not loyal to the rulers Y. Okay, like this you need to represent this sentence. People only try to assassinate rulers they are not loyal to. Next example. Marcus tried to assassinate Caesar. So there is no multiple statements in this one. That's why there is no need of using all symbol or there exists symbol. Sorry, all symbol and there exist. So simply you can write like this. Try to assassinate. Okay, try to assassinate. Okay, who is trying to assassinate whom? Marcus is trying to assassinate Caesar. So I will write as Marcus and Caesar. So the way of understanding will be like this, you see. Marcus is trying to assassinate the Caesar. Like this we need to understand. Okay, now with these all representations, sometimes what happens, a conclusion, a inference will be given to you. What is that here? The inference is, was Marcus loyal to Caesar? Okay, generally what happens now, right? If you skip this was for time being, so what it will be? Marcus loyal to Caesar. So you can simply represent the statement as loyal to. Who is loyal to whom? Marcus is loyal to Caesar. Like this you can represent. But what about this was? We are asking some question. So with the statements, previous statements, we need to prove that whether this Marcus is really loyal to Caesar or not. But for generally what we will do is, we will try to keep the negation here. So if we keep negation, what happens? It will become that not loyal to, means Marcus is not loyal to Caesar. But we are not guaranteed whether he is loyal to Caesar or he is not. We cannot guarantee. Why? Because until and unless we prove it, you cannot directly represent the question in this way. Okay, right? That's why this kind of representations does not work here. So what we have to do is, we need to perform some transformation. Transformation means we need to convert this particular sentence in goals. We can say one goal. What is our goal? We need to prove that Marcus is really loyal to Caesar or not. This is our goal. So what we are doing, we are trying to split this goal into different possible set of goals, and we have to go on proving them. Okay, when we stop it, whenever we reach to our specific goal, right? So what are the representations we have to do is, this will be in this way. First of all, we need to identify that Marcus is a person. Then we need to say that he is trying to assassinate. Marcus is trying to assassinate some Caesar. And also we need to represent who is this Caesar also. Why? Because Caesar there is also having some relation to the Caesar. What is that? Ruler. Means if you could able to use this sequence of statements, so simply we can prove that was really the Marcus is loyal to Caesar or not. Coming to the most important attributes in the predicate logic. When you are talking about predicate logic, two important attributes comes into picture, which is called as instance and easy. These are the two attributes which we will be used in order to implement some reasoning or in order to show some reasoning, which is nothing but called as some property inheritance. Okay. Let us try to take some example and we will try to understand how this instance and easy can be used. So generally what happens, these are explicitly used in order to express or to capture the relationship. So simply we can say that it can be a class membership, or we can say that it is a class inclusion. Okay, once we get an example, it will be very easy for us to understand. Okay, so what is the example? I will take an example here itself. What is that? I am trying to represent the statement like this. What is? Kohli is a cricketer. Kohli is a cricketer. So here, why I am taking this one? So this representation will be like this. Is a, okay, is a Kohli, comma, cricketer. So what I am talking about? Talking about Kohli. So what I am telling about the association. What is that association? Is a. So is a attribute. Is a attribute which is showing the relationship between the Kohli and the cricketer. Okay, we will have some more examples and we will make it clear how this is a and how this instance can be used. Okay, here instance, what is instance? Instance is a binary one. Just like here, is a is also binary one. Why? Because we have taken two parameters inside the parenthesis. Similar to that one, even if you take instance, means in place of is a we are going to use instance. If this instance is a binary one, then it is also going to have two parameters inside. So one parameter is the object, means first argument will be the object and the second one will be the class to which the object belongs to. Okay, I am repeating once again. You see, if the predicate, if I say this instance is a predicate, then this predicate should be represented in the binary form. This binary form is going to have two attributes inside. One attribute is an object and another attribute is the class to which that object belongs to. Now try to see these examples. Marcus is a man, so I can represent like this. Marcus is a Pompeian, like this. Here what happened? All Pompeians were Romans. All Pompeians were Romans. Here Caesar is a ruler. Caesar is a ruler. Now about this one, all Romans, okay, all Romans are either loyal to Caesar or hate Caesar. Now here what is happening? We are trying to explain this predicate logic representations into the English representations. In the earlier slides, we have taken the English representations and we tried to convert them into predicate logic representations. That is the only difference. Okay, but remaining things are same. But now our concept is not to represent these sentences in the predicate logic form, but by using the attributes like is a and instance, we need to see how this can be represented. So here what is instance? Instance of Marcus comma man. So here what is happening here? We are talking about a specific world. In this world there will be multiple mans. Okay, plenty of mans will be there. So what I am telling here, man is a Marcus is a man. Marcus is a man is nothing but Marcus is the instance of this particular world. So what is this world here? Man can be the world. Whenever I say man, there will be multiple mans. Okay, we can say that there are multiple instances of man. That's why by using the instance representation, I am representing the sentence, same sentence, the first one in this manner. Marcus comma man. Instance of. Similar to that one here you see Marcus Pompeian. So to which world I am talking all about? I am talking about the Pompeians here, not the man. I am talking about the Pompeians. In this Pompeians, what is happening? Among the Pompeians, Marcus is one. So I can say that here Marcus is an instance. Marcus is an instance of a world which is called as Pompeian. Okay, for example, if you talk in terms of predicate, now what happens? This instance is going to become a predicate. This Marcus is an object and Pompeian is the class to which this object belongs to. Similarly, I have tried to represent all these statements by using instance. You try to observe, instance means it belongs to a particular word. Okay, if it is man, and if we are talking about a specific man, then we can say that it is an instance. In the previous example also, we have represented Kohli is a cricketer. Okay, means among the cricketers, I am talking about only one particular one. So, I can represent the same sentence in this way. Instance, here the first parameter should be object. So, I can write as Kohli. And the second parameter should be the object to which the class belongs to. So, to which word the Kohli belongs to? To the cricket. So, I can say that cricketer. Like this also, I can convert the representations with the help of some instance attribute here. Okay, what about is a? Is a also some same kind of things here. The same thing, instance and is a. So, what is the meaning of this is a here? Means Pompeian is a Roman. In the earlier case, Kohli is a cricketer. When Kohli is a cricketer, we are writing is a as a predicate and the first parameter is Kohli and the second parameter is cricketer. Similar to that one, if I represent is a here, so what it means is, it means that Pompeian is a Roman. Pompeian is a Roman. So this English representation I am trying to convert into predicate logic with the attribute called as is a. Okay, this is a way how we need to understand how to represent the predicate logic representations with the help of instance and a is a attribute. Now coming to the other point, which is called as computable functions. So before trying to tell what these computable functions are, we will try to see the same kind of examples and we will try to observe where these computable functions are really required for us. Means with these examples, with these representations, we need to understand first of all what is a computable function and where generally these computable functions are applied or used. So Marcus was a man, the same statement. So as we are having some kind of knowledge, so I can say that man Marcus. Man Marcus. Marcus was a Pompeian, the same thing. So I can write it as Pompeian. Who is Pompeian here? Marcus is the Pompeian. Marcus was born in 40 AD. So first of all, we need to observe the things. Marcus born and 40 AD. Three important points are there in this. So which one are the objects and which one is going to be a predicate? Predicate is nothing but here showing the association between the objects. So I can consider born as a predicate. Who born? Marcus. When he born? On 40 AD. Okay, right? All men are mortal. So in this case, again the same thing. All. Okay, why I am using X? I am using X in order to represent the men. So it is men. So who they are? They are mortals. Who are mortals here? X are the mortals. Next you see, all Pompeians died when the volcano erupted in 79 AD. All Pompeians died when volcano erupted in 79 AD. So all Pompeians, when it is all Pompeians, we are going to write again for our X. But before that, this representation should be done. Erupted. What is erupted? Volcano erupted. So we are going to form in this way. Erupted. Okay. What erupted? Volcano. Okay. Volcano. In which year? In 79 AD. That is one thing. The next thing is all Pompeians were died. All Pompeians. The same representation. Pompeians. What happened? They have died. Who died? The Pompeians died. The Pompeians died. When they died? In 79 AD. Okay, the same way what we have done for the previous representations, in that same way only we try to represent it here also. But now you try to come up here. We are talking about a year. No mortal lives longer than 150 years. No mortal lives longer than 150 years. Means I am talking about the time period. Okay, time period, or we can say that specific time. Okay, whenever it is the case, it will be very difficult. By using predicate logic symbols, we cannot represent this sentence. So what we are doing, we are taking the help of these computable functions. The best examples for these computable functions are GT and LT, greater than and less than. So for representing this one, we need to understand this one. You see, greater than. No mortal lives longer than 150 years. So here, first is I am talking about all the mortals, and I need the time periods. Why? Because I need to decide whether they have really lived longer than 150 years or not, or they lived below 150 years. So for that one, definitely I need to know the difference between the time periods. So for one time period, I am taking T1, and another time period I am taking T2. Very simple. If I want to know how many years a particular person was alive, then I need two years. One is the born year and another one is the death year. So I will try to find out the difference between them. Means I will subtract the died year with the birth year, and I will get some value. So that value represents that these are the number of years the man has lived. Similar to that one, here also I need two time periods. That's why I have taken T1 and T2. What is that T1 is talking all about? Talking about the born, when he born. Okay, and the T2 we are talking about death. Born and dead. So we are going to check the greater than. GT greater than. GT means greater than the T2 and T1. So for example, if this person died in 2022, the person lived in 1950, the person born in 1950. So what happens? It will become GT of 2022 minus 1950, 150. So how it will be? It is going to simplify like this. GT 70, means the difference between these two. Okay, 70, 150. 70 is greater than 150. Is it true? It is not true. It is not true. Like that you have to simplify the things. So whenever I want to prove that no mortal lives longer than 150 years, definitely I have to use these kind of functions. So here, that's why here we are calling GT as a computable function. Okay, whenever you want to do the comparison between the values, or whenever you want to get the difference between the two time periods, like that, you have to use the computable functions here. Okay, and the seventh one, it is now 1991. So there is no any logic included in this one. So simply I can write it as now equal to 1991. Okay, so next one, alive means not dead. Alive means not dead. So here also we are talking about some time period. We need some time period. So but we are not seeing that how many number of years that a person has alive. We are just talking about the time period. So instead of taking T1 and T2, just we are taking it as T. First we are trying to see whether they are alive or not. Alive means alive. Who is alive? Some people. X. Okay, at what time? Here this symbol I have used. Why? Because here in the representation, in the English representation, there is not. Okay. Ninth one you see. If someone dies, then he is dead at all later times. Okay. That means that again we are talking about two different time periods. So the same kind of thing, again we have used computable functions in this case to represent the knowledge. Or to represent this English sentence in the predicate form. Now let us talk about the last objective of this video session, that is the well-formed formulas. Okay, in the propositional logic or in the predicate logic, whatever the fact you represent which is related to some real world, then we can say that it is a well-formed formula. I can say it is raining is a proposition. I can say I can say it is raining is a well-formed formula. I can say James is hardworking is also WFF. Okay, so how this WFF is specifically represented means if you want to represent any English sentence as a well-formed formula, remember you need to consider or you need to take care of variables. Means your well-formed formulas should have the variables. It should have some parentheses and it should include some logical connectives. We can say some connective symbols or we can say that some logical operators. Okay, most of the logical operators we are going to use is either negation, conjunction, disjunction, implies or double implies. Okay, right? It should have variables. Means well-formed formula should have variables. It should have parentheses and it should have some symbols. Here symbols are nothing but some logical operators. How many types of WFF are there? There are two types. Already I mentioned it. One is called as simple or atomic sentence. Means a sentence which does not have any connectives. A sentence which does not have any connectives means I can say that P is a one atomic sentence. P can be anything. James is hardworking, it may be. It is raining, it may be. Right? Any sentence we are using some variable to represent it. If I say P, that means that P is talking all about a one particular sentence. So I can say that it is a simple sentence or statement or atomic statement. P can be an atomic statement. Q can be an atomic statement. Right? R can be atomic statement. Right? These can be atomic statements. But remember, P and Q cannot be an atomic number. Atomic statement. Why? Because it is having some connective logical symbol. Logical operator. An atomic statement or simple statement should have only one, that is variable. It should not supposed to have the connector. Next one, composite or we can say that molecular statements. James is hardworking and James is intelligent. James is hardworking and James is intelligent. So in this case, what is happening? We are trying to combine two different sentences. Two sentences into one. Okay, if I say James is hardworking, so I can represent with a variable as P. If I say James is intelligent, I can represent it as Q. So what I am telling, James is hardworking and James is intelligent. I am using a word, connector. What is that? And. So you should suppose to use some conjunction in between these two. So what happened? It became P and Q. So here we are talking all about two different statements, or we can say two statements, two atomic statements we can say. Means whenever you try to combine two atomic statements with the help of some connectives, we can say that it is either a composite statement or it can be a molecular statement. See, these are the some of the examples, right? Not P, not Q, P or Q, P and Q. These are all the valid statements only. But we need to decide, means before deciding that these are valid, we need to know which one will be considered as valid and which one are considered as not valid. Why? Because simply by seeing the showing these examples, I cannot say that this is a valid statement. I should suppose to give a specific reason, right, making it as a valid statement. So we will try to take some of the sentences and we will see whether they are really valid as per the rules of the well-formed formulas. Then we will decide whether these things are valid statements or not. But remember, before proving that, means if I want to prove P and Q is a valid statement, then before that I need to prove that P is valid and I need to prove Q is also valid. Then only I can say that P and Q is also valid. Means individual validation is required as well as the combined validation is also required. Okay, we will try to see some of the examples. Okay, right, in this case you see P and Q. When can I say that P and Q is WFF? When these are all also WFF only. Means P should be WFF and also Q should be WFF. Of course, it can be an atomic statement or it can be a composite statement, but definitely they should be valid. Now we will check the validity of these statements. I have represented P in the brackets, in the parentheses. Now can I say this one as a valid WFF? I should not supposed to say. Why? Because individual statement, means atomic statement, cannot be placed inside the parentheses. Individual statement or an atomic statement cannot be placed in the parentheses. So that condition, this statement is failing. So I can say that it is invalid WFF. It is invalid WFF. Now come to the second example. Not P and Q. Not P and Q. So it is also not a valid statement. Why? Because whenever you represent this one, it does not. It may mean that, means your intention may be like this. Your intention may be writing of this sentence like this, or sometimes your intention may be in this way. Because there is lot of difference between these two representations. But here what is happening, whenever you are representing not P and Q, right, we are not guaranteed that whether you are talking all about this kind of representation or this kind of representation. Some sort of confusion is there here. You should not supposed to keep such kind of confusions while representing the WFFs. That's why I can say that this is not a valid statement. It is also an invalid. Now come to the third one. Third one, P implies Q. Right? Whenever there are composite statements, remember, whenever you are using a composite statement, definitely you have to keep that one inside the parenthesis. But here what is happening is, unnecessarily we are using double parenthesis to represent the composite statement. Okay, how it should be? It should be either like this. P implies Q with only one parenthesis. Means here this will becomes an invalid statement. This will become an invalid statement. And coming to this one, this is also not a valid one. Why? Because just now I told that if it is a composite statement, then definitely they should be placed inside the parentheses. But here we didn't mention any parentheses in here. We didn't mention. That's why even this statement is also not a valid statement. So while mentioning the WFF, you need to check all these kind of representations. Then only we can say that WFF is a valid one. Coming to here, P double implies Q. So what do you mean by here P double implies Q? Right? P implies Q is okay. This is a valid statement. But whenever I say P double implies Q, I should not say that this is a valid statement. Why? Because you should not supposed to use two double implies at the same time. Okay, so again this one is also invalid. Next, coming to the fifth example, P and Q and Q. Right? So here what is happening? You see here you are using a connector. Of course, the usage of connector in this case is okay. You are trying to connect two atomic sentences with this connector. But what about this one? Whenever you are keeping Q outside the parenthesis, that means that it became an individual atomic sentence. But this is used to represent the composite statement. Atomic and composite. You are using in a different way. So we can say that this one is also invalid. Come to the sixth example. PQ. Of course, in this case, means in this particular case, our representation is correct. Why? Because P and Q represents the composite statement. The composite statement, as per the rules, we have kept inside the parenthesis. But come to this one, PQ. P is one atomic sentence statement and Q is also another atomic statement. Two atomic statements without the use of connector, you should not supposed to represent. Means this type of representations is not permittable. Either you have to use P and Q or you have to use P or Q. Like that it should be. But here, without using a connector, you are trying to mention or represent two PQ in the same place. Okay, that should not be happened. So here, this is also an invalid statement. Coming to the other example, P or Q. Okay, P or Q implies and Q. And Q. Just now I spoke to you that and is a connector. If you are using a connector, definitely there should be two statements, two atomic statements should be there. But here there is no any statement. Okay, that's why this statement, this thing is also will becomes an invalid. Means whenever you represent a specific statement and say that it is WFF, then it has to satisfy all these kind of rules, we can say. Then only we can say that it is a valid representation. Okay, so come back. With this, we can simply say that all these statements are valid statements. Why? Because they are satisfying all the rules we have discussed so far. Okay, so this is all about the concept of well-formed formulas. We will try to come up with a new topic in the next session. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.